Hello everybody. I apologise for the break in this presentation. I don't really know what just happened. My recording program just went and glitched on me. So anyway, let's keep going from where we were. So we just finished talking about phonetic gradualism and punctuated equilibrium, and now we're going to look at an example of how speciation actually occurs. So this is our model here. So if you look, we have a species that's going to appear here. Okay, on the southern side of the Himalayas, and our species is going to go in two directions. One group of the species is going to go eastwards around the Tibetan Plateau, and the other side of the species is going to go westwards around the Tibetan Plateau. And so what we're going to see is, as the species progresses further east and further west, we're obviously going to see that it becomes more and more different to the original parent species. Now, species that are next to each other, so B and A or B and C or C and D, can interbreed with each other. However, the more distant species are from one another, the more difficult it will be for them to breed with each other. So D and B would have a lot of difficulty with successfully breeding, but B could breed with C, and B could in theory breed with A as well. But C could not successfully breed with A. Okay, so what we begin to see is, as we move both eastwards and westwards, we can see that the species that appear are going to get more, and so you're going to become more and more different when compared to the original parent species. Okay, we're going to see that as we move this way, A can breed with F, F can breed with G, and this way B can breed with C, C can breed with D, until eventually we make it all the way around the Tibetan Plateau. And at that point we end up with species H and species E. Okay, now they're obviously the most different to the original common ancestor down here. And obviously by this point they are significantly different from each other, and species E and species H will not be able to interbreed. They will be completely different species. So what we have here is we have a situation where we have microevolution, lots of steps producing lots of individual species, which in the end can possibly lead to a macro evolution effect, okay, which produces essentially completely different species which are incapable of breeding with each other. It may even produce different families. So by the time we get over here, we may have different genuses altogether. Okay, now this is going to be a case of phonetic gradualism in this model. We have lots of minor changes gradually accumulating, which will lead to a new species gradually arising. Okay, so in this case, there's been no sudden shift that's caused, very rapid evolution. So let's think about the types of evolution that there are. Well, there's three of them. There's divergent evolution, convergent evolution, and parallel evolution. So paleontologists refer to an ancestral species giving rise to diverse descendants as divergent evolution. So an impressive example is the divergence of an ancestor species that gave rise to a varied range of animals, including platypuses, armadillos, rodents, bats, primates, whales, and rhinos. So it's actually a whole group of mammals. So think about it. All mammals are related to a kind of a mammal-reptile hybrid creature that kind of made its appearance around the end of the Permian, approximately around 252 million years ago, and it's part of a group of organisms called the therapsids. Okay, and so all mammals evolved from that species. Not sure exactly which species it was, but one of those species around that time. So just think about that. Every single type of mammal you can think of has evolved from that species. So that's pretty amazing, and that's an example of divergent evolution. You have multiple different ancestral species, essentially, which are very diverse from the original parent organism. So here's our model down here. Here's our common ancestor. And this common ancestor, through evolution, gives rise to multiple diverse organisms, species, genuses, families. And so this is an example of divergent evolution. So divergent evolution produces descendants that are markedly different from their ancestors. In contrast, convergent and parallel evolution are processes whereby similar adaptations arise in different groups. They differ in degree, but can be difficult to distinguish from one another. So let's think about convergent evolution. Well, convergent evolution is a situation where we get the development of similar characteristics in distantly related organisms. So let's look at an example. So in the case of convergent evolution, a good example would be, well actually no, do you know what, let's do parallel evolution. In the case of parallel evolution, you get the development of similar characteristics in closely related organisms. So it's just a reflection of how closely or distantly related the organisms are. If they develop similar traits and they're distantly related, it's convergent evolution. If they develop similar traits and they're closely related, it's parallel evolution. In both cases, similar characteristics develop separately because the organism in question adapted to comparable environments. So an example of convergent evolution is sharks, ichthyosaurs, and dolphins. They are morphologically similar. Their body shape is the same, even though the origin of each of these species is separated by millions of years. So let's go to the next slide. So here's a dolphin. We're all familiar with that one. So dolphin is a mammal. Here's a shark. Shark is a fish. And here's an ichthyosaur. That's a reptile. So sharks made their appearance all the way back in the Devonian. That's 400 million years ago, give or take a little bit. Dolphins, on the other hand, they're relatively recent. They will have popped up sometime in the last, give or take about 10 million years, maybe even 15. And ichthyosaurs were around in the Triassic and mostly into the, well, actually, they mostly lived in the Jurassic. So they're going to be somewhere in the region of about, give or take a little bit, 175 to maybe 100 million years ago. Okay, so you can see these species are essentially different in when they first appeared. So there's a large spread in terms of their temporal relationship. But what you'll notice is the basic body design is very similar. You have a pointed face, essentially pointed nose. You have a fin on the back. You have two flippers on the front for steering. You have a tail for propulsion. Okay, and then you have the smaller hind limbs, residual hind limbs there. In the case of the dolphins, they're nearly completely gone. You can't see them. So the obvious question is well, why? Why are these organisms so similar, despite the fact they are so distantly related to each other? And the answer is quite simple. This body design works brilliantly in water. Because it works so well, it just keeps turning up again and again and again. Evolution will keep going back to the design that works best. And so, essentially, even though these species are not closely related at all, morphologically, they appear very, very similar. So that's an example of convergent evolution. Very distant organisms taking on essentially the same basic design. So now we need to think about parallel evolution. That's the development of similar characteristics in closely related organisms. So here's a good example of parallel evolution. Elephants, mammoths, mastodons. So what you're going to notice is essentially they develop relatively similar designs. Large bodies, large trunks, tusks, ears, everything, the basic body design is very, very similar. Okay. Now there are minor differences. You can talk about the ears obviously being smaller for the mastodon and the mammoth compared to the African elephant we can see here. In the case of the mastodon and the mammoth, the tusks are longer. You obviously talk about the hair as well, but the same basic design reappears again and again and again. And that's because these organisms, number one, share a relatively close common ancestor, but they've gone off on their own trees. They've gone off on their own branches of the evolutionary tree. Okay, they're not on the same branch. They're off. Each one of these is off by themselves. So the fact that they keep coming up with the same basic design is a reflection of a recent common ancestor, but also it's a reflection of the fact that they all essentially exist, all function in the same way. Each one of these organisms is essentially, going to gather its food in a very similar way to the other. So a mammoth is going to gather its food in a similar way to an African elephant and a mastodon. Therefore, the same body design, essentially persists, and, the same adaptations will appear because they're doing the same thing, just in slightly different environments. So that's an example of parallel evolution. So, as we've already discussed, evolution, most evolution takes place in what we refer to as a mosaic fashion. It's referred to as mosaic evolution. So, to put it another way, evolutionary change does not involve all aspects of an organism at the same time. If something is working, there is no evolutionary pressure to change it. So, change is driven by selection pressure. There's something about an organism that gives it an advantage, and therefore that variant makes it more successful. So there's a pressure that makes that variant more successful. And this means that key features associated with a descendant group may be present. So even though the organism is becoming more and more different from the descendant group, if there is some part of the body that functions perfectly and does not need to change, there's no selection pressure, it won't. So, for instance, birds have feathers and fused clavicles. A clavicle is the wishbone. And these features are shared with the earliest birds / dinosaurs. So, feathers work perfectly. The latest research suggests that, dinosaur feathers were almost the same as modern bird feathers. So clearly the design was perfected all the way back, 100 million years ago. And since then, there's been relatively little requirement to change. Also, fused clavicle. So a clavicle is essentially your collarbone. So in the case of birds, they're fused to produce that kind of like V-shaped bone that you might occasionally take out of the chicken. Okay, and that's a design that's shared with early birds and dinosaurs. Once again, it works perfectly. It meets its requirements, and so there's no selection pressure to it for it to change. So here we go. So this is Archaeopteryx. So this is a very early bird. Well, there's a bit of a disagreement. We probably think Archaeopteryx is probably more of a glider than a flyer. And here we have a modern day bird. So you can see here's the fused clavicle. So that's the wishbone there and there. Okay. Obviously the body would be covered by feathers, but there have been certain changes. Okay. So for instance, the tail's gone. The tail obviously clearly going to cause misbalance when flying. The weight of the body is going to be incorrectly distributed with a tail sticking out the back. And so you can see in modern day birds, the tail is now nearly non-existent. We can also see that the forelimbs have been simplified to save weight. Getting rid of bones means the forelimbs, the wings are now way less, and so it makes it easier for the bird to take off. So we can see the forelimbs have changed. There wasn't evolutionary pressure to do that, making the body lighter, and therefore, meaning you have to expend less energy to actually fly. And we can also see there's a slight shift in foot design. We can see that, we still have the free front-facing toes, but this toe has essentially moved to a rear position. Okay, and that's important when it comes to, number one, gripping onto branches, but it's also important when it comes to landing. It means that as you land, the weight is spread over the whole weight of the foot rather than just on the front three toes. If they were to land on the front three toes, if a bird landed like that, chances are they would break them. So we can see that, changes have occurred as selection requires them to occur. In the case of the clavicle and feathers, they work perfectly, so there's no reason to change. So mosaic evolution is when you change, one or more characteristics at a time. So organisms organisms have evolved recently some characteristics, while other features are retained from the ancestral group. So, the birds are a lovely example of mosaic evolution. Some things have changed, like the forelimbs, but some things have been retained, like the fused clavicle. I mean, as I said, it makes sense. Why would evolution happen if the feature in question performed its job well? There would be no pressure to make that change. So now we need to think about evolutionary trends. So if sufficient fossil material is available, paleontologists can determine an organism's evolutionary history, also referred to as its phylogeny. So they can determine evolutionary trends, so changes in a specific feature or features over time. So, we can look at some species like ammonites. These are a very, very common species. Once again, we'll discuss them more when we look at Mesozoic evolution. And ammonites, essentially, they're a group of cephalopods. That's the group that includes octopi and squids. And ammonites essentially have a coiled shell, and they evolved increasingly complex shells over time. So as we look at the shell design for the ammonoids, that's the group that includes the ammonites, we see over time the shell becomes more and more complex. We can also see that in animals. So when we have the titanotheres, that's a group of rhino-like animals that lived on grassy plains during the Eocene. Okay, and over time we can see changes in body shape, horn shape, etc. Now, in the case of both of these examples, we can see these changes gradually occurring because we have a really good fossil record for them. So here we go. So here is an ammonite from the Triassic, and here's an ammonite from the Cretaceous. And you'll see, although the basic shape is the same, you'll notice that these suture lines, these marks here, are getting more and more convoluted, more and more complex. And so that tells us that this is essentially a later ammonite compared to this one here. And these are the titanotheres up here, and you can see, so this is the Eocene. So we have the early Eocene down here kicking off about 56 million years ago. We can see this is the basic design, and we can see slowly but surely the build becomes heavier, the head shape begins to change, and by the time we make it up here to the late middle Eocene, we can see the nasal horn beginning to develop, and by the time we're up here in the late Eocene, we have this essentially this bifurcated nose horn appearing, and they've taken on a very heavily built rhinoceros-like form. So once again, as long as we have a good fossil record, we can see these changes happening. So evolutionary trends are complex, they can occur at different rates, and in some circumstances they can appear to be reversed. So a good example is natural horses have been steadily getting bigger. However, some Cenozoic species displayed a decrease in size. So on the whole, throughout the Cenozoic, horses have been getting larger and larger and larger. However, every once in a while, some horse species actually go backwards and they develop to be smaller. So these adaptations could be considered as having resulted from a change in the environment. We've already, gone and spoken about how if food gets scarcer, it's often advantageous to have a smaller body. So it could be a question of the amount of food, or it could be an attempt to exploit a new habitat. So if the horse is trying to go from a grassy plain into a forested area, well, being a really big horse trying to run through a forest is actually a disadvantage. There are lots of trees in your way. You have to be able to turn quickly. You have to be able to zig and zag. So being a big horse, well, that's not actually that helpful. In that situation, being a small horse is more advantageous. You can get between the trees more easily. You can turn more easily. It makes it easier for you to escape if you're being chased. So, there could be any one of a number of reasons why, stepping back and going for a smaller body size might make evolutionary sense. And we've already discussed that some organisms show very little obvious change. These are often what we refer to as the living fossils. And so, for instance, we have the fossil Lingula, and that hasn't changed, that should say since, I do apologise, the Ordovician, and, that's a bit of a mistake there. That's very, very wrong. That should say about 420 million years ago. So there we go. One paragraph, two mistakes. My apologies. So here are some examples. So here we go. So this is the coelacanths. This is a fish called a coelacanth. There's a modern example there. Now, to be honest, this one's been pickled, so that's why it has that strange white colour to it. But this is an example of the fossil from the Devonian. So that's approximately 400 million years ago. The same basic body design has persisted all that time. Horseshoe crabs, once again, in this case Ordovician. So we're looking somewhere in the ballpark of about 420 million years ago. Modern day horseshoe crab here. And then we have Lingula. Lingula also pops up in the Ordovician, so approximately 420 million years, during which time it's undergone very, very little change. So these are living fossils. And the reason they haven't changed is simply because their body design meets the requirements for the environment in which they are living. So there's no selection pressure. So nothing is making their body design change, and so they don't. So it is difficult to evaluate change that's happened to soft tissue as it's rarely preserved. So if we go back and we look at, the horseshoe crab or the coelacanth here or the Lingula, these fossils here are the hard parts of the body. The soft parts of the body, the muscle, the gut, the reproductive organs, they've all decomposed and they've been lost. So when we compare these fossils, what we're doing is we're only comparing the hard parts. So it does mean if there's been some kind of minor change to muscle structure, if the organism evolved to use a new digestive enzyme, or if the organism developed a new kind of immune system, we would never know about it. So when we're talking about living fossils, we're bearing in mind that we are only looking at the hard parts of the fossil. Oh, went the wrong way there. So living fossils either live under a wide range of conditions, so they're very generalized, like Lingula. So it lives everywhere, so essentially it's taken on this very generalized body shape. Or they live in a very limited environment that hasn't changed much, like horseshoe crabs. Horseshoe crabs tend to like to live in relatively warm, shallow water. And so they are perfectly designed for that environment, so that once again, there is no selection pressure driving change. But surely if we wait another 100 million years, some change would occur. After all, evolution is random. So only the first stage of evolution is a matter of chance. So variation is a matter of chance. What happens when two individuals produce an offspring? What happens when two individuals produce an offspring? Will a mutation be beneficial or will it be harmful? So the second stage, natural selection, is not random as it favours those with variants that enhance an organism's chance of survival or ability to successfully reproduce. So there's actually something that controls the second stage. The first stage is blind luck. Okay, does a random mutation suddenly pop up from nowhere, or how does the genetic material from the father and the mother get shuffled to produce an offspring? So that's random. Once we get into natural selection, it's not random. There are selection choices that are being made based on forces. So if natural variation hasn't produced any beneficial variations, the organism will not change. So these organisms are pretty much perfectly designed for their environment, so they've got no reason to change. So every time an adaptation turns up, chances are it's actually going to be harmful. It's going to make the organism less competitive. And so that organism is more likely to be less successful, and it's less likely to reproduce. And so chances are that particular variation will not begin to become a dominant variant in the species. Okay, so there we go. So I haven't actually done the code word yet. The code word for today is gold. That's G-O-L-D, gold, as in the metal. So, alright, so I'm very sorry this presentation was in two pieces. I don't know what happened to my recording software. Once again, I apologise again. Keep an eye out for the second half of this, well, keep an eye out for the next presentation, and take care.